A, the time slot, and B, for agreeing to participate in this. And it's interesting, I keep saying it, I've known Ian for many years now, and it's the things you don't think about that usually come and bite you on the you-know-where. And certainly on the power systems, some of the histories, maybe later on we'll tell stories of having two vehicles stuck that could not move one way or another and blocking the front entrance to the Angerman base in Kabul because the electrics and the power just all failed. And these are lessons learned, and these are manageable issues along the way, but in many cases from an operational perspective they're not considered fully until you learn the lesson. And my experience with many times with Ian outside building equipment for our vehicles, the Australian government, it was lessons learned and fixing them up. So Ian, please come and join. We look forward to your presentation.
Thank you. Thanks very much, Rob. As Rob's already said, we've known each other for quite some time, and over a period of time the things that happen in the field have been very distinct in terms of power. So it's quite an apt point. Rob and I talked at this symposium seminar last year, and we go to hundreds of these probably over the lifespan of my company, and I've never seen an electrical presentation. And I basically said, do you fancy one? He said, go on then. So here we are, and we're going to give you a presentation on electrics. What I'm going to try and do is give you basically an overview to start with, nothing to do about what I do, but how armouring is going to change your car. So basically, not a great deal about me. I've been working on the vehicles for around about 40 years in various different guises. And vehicles, I mean aircraft as well. So I came from the RAF, I came from avionics. So I worked on radars and electronic countermeasures. And then since about 1990, I've basically worked on cars. I've tested and developed prototype cars for various different organisations, military, civilian, police, etc. And for the past 20 years, we've run our company, which specialises in some very key aspects of electrics, electronic countermeasures, electromagnetic compatibility, and various things like that. So the aim today is I'm going to give you an introduction into something which is often missed, in the fact you're going to armour a car. And it's nothing to do with electrics or electronics. And in actual fact, by the process of armouring the car, you are going to basically destroy a lot of the functionality of the electronics. And you won't even know some of that. And I can't even prove some of that, but it is very, very close. And I'll explain that as we go. So I'm going to highlight some specific areas which may be affected by up-armouring a vehicle. Then we're going to look at something that Rob sort of intimated on, a specific case study which happened in Afghanistan around about 14 years ago. So it still happens now, and it still happens in different locations around the world. And then we're going to basically look at what we've learned electronically about the Land Cruiser 300 since its release last year, and subsequent stuff that has happened in testing purely from an electronics, RF, antennas perspective, nothing from an armouring style side of it. So when we actually come to armouring a vehicle, end users, procurement people have various different things. But basically, the OEM company, whether it is Toyota, in this, we've got Toyota here, whether it's Mercedes, whoever it's, and they've spent millions of pounds in R&D. And that time has been spent by years of development, accumulating data like Justin was saying, and collecting physical data about what's going on. And also their supplier base has done the same thing. So when you actually come to the vehicles going into service, they then collect reliability data, and it is billions of hours. Now, it doesn't seem like it, but we're getting reports back from showrooms and maintenance facilities from Toyota, etc., around the world, and basically they have got that data. And they continue to do R&D, and they're also responsible for homologation and testing. So these vehicles are, to all intents and purposes, safe, from what we want to know. And you, as or people who are buying in vehicles, probably want the same sort of thing. But you want it to be risk resistant to threats. You're going to armour it. You want it to blend in. It's going to be white, probably. It's going to be comfortable still. I'll come back to that in a second. Safe, reliable. Multi-role, we've heard of quite a few bits and pieces on that. And probably still legal. That's very, very debatable. But we'll get on to that. Comfortable, as you can see, I'm not the normal percentile person. And when somebody does want to put body armour on somebody and try and get into a vehicle, they usually ask me, and you don't want to see me get into an armoured vehicle with my legs in the air and various other things. And it's, you know, the space in them is obviously reduced. So how do we achieve this, or how do the armourers actually achieve this? Well, first of all, they're going to rip out the complete interior. That's a large percentage of all the wiring, all the electronic control units that are inside the cockpit area, etc., all the displays, all the control systems, and they're all going to come out. And you saw a slide earlier on of a vehicle which is basically just armour under refurbishment. So at that stage, you know, you've taken out everything that the OEM has basically spent a long time working on. You're going to change the external skin. Some people might want hatches in and various other things like that. And then you're going to install some specific armour, cockpit area, maybe into the engine bay. We talked about radiator armour. We will talk about battery armour. Please don't, but we'll get onto that. And you're going to alter the internal dimensions of the cockpit area of the actual armoured vehicle, quite significantly in some stages. The armourer is going to have to shorten cross members. They're going to have to do all sorts of different things to fit all of this equipment back into the shortened spaces. Seats are going to be higher, all sorts of various things. And they're going to put it all back together. Now then, from an electrical point of view, and I'm only going to talk about electrical because lots of other things are actually now invalid. Braking distances might be, crash zones have gone, crumple zones have gone, and various other things. But it basically puts all of the information that the OEM had on the electrical side in doubt, because basically we ripped it all out, we've thrown it all back together again, and in some cases we haven't even put it back in the same place it came from. So electrically we have a lot of problem there. All that test and development data, let's start again. We have our vehicle, and electrically we've got to start again gathering information about how good it is. And we've changed a number of the parameters of the vehicle. From the mechanical side, as we've done it, we've actually changed centre of gravity. That does affect some of the systems on board and how they react. We've certainly changed braking distances, and I have figures from various things that I've done. The momentum, the amount of energy that's needed to do certain things has all changed. And what we don't know is whether the performance of the electronic and electrical systems were in the parameters to which they were designed for. And by collecting a certain amount of data, we are very, very close on vehicle ranges that things can work on. But basically, we don't actually physically know. And the big one is, again, intimated yesterday about radiator armour. We're actually destroying the cooling effectiveness of certain areas. And even inside the cockpit itself, inside the internal part of the vehicle, it's getting hotter. We've just been out in the Middle East doing testing, and even with the air conditioning on, we're still in the 30s, 35 degrees. So it can get very, very hot. So we're changing the operating ranges. I'm going to go into some of the specifics in a minute. We're going to actually also, when we put things back together, the chances are we're going to change the position of sensors and ECUs because they're not going to be in the same position. Weight loading has changed, especially front to back or left to right in terms of the armouring. And a big one is the wiring harness location is going to be different from the main vehicle itself. It's going to be higher. It's not going to be on the main bodywork. Often it has changed. And there are many, many examples of electrical failures in in OEM cars in civilian world, where they build vehicles and all they have to do is move that physical wiring harness 10 centimetres and it fails homologation. So there's a lot of issues with that. And also, one of the big ones from power is you're now losing all your bond points and earth points inside the vehicle, and they're now going onto an unproven metal sheet of body armour. So, armour within the vehicle. So you're actually making new earth points and bonding points. So, possible systems affected. Airbags. So, a very brief thing about the airbags. Airbags are calibrated on various different things within the electrical and electronics. First of all, their distance from the actual person within the vehicle is crucial. We will have moved, guaranteed you'll have moved the seat up. You're compressing the internal space. The side airbag, as you see there, comes out very, very quickly and is very, very close. If you're moving closer to that, you may be within the deployment range. Things like this are not physically known in this particular instance. The chest distance, 25 centimetres, is normally the chest to the airbag. You know, if you have got seats that have moved forward and you've moved stuff back from the firewall, you're reducing that space. And certainly for people like me, it becomes quite impossible sometimes to actually get into the space. So airbags require certain calibrations, and we know that we're very, very close to being on the edge of how airbags would react. So if you're in a car which is armoured, the issue is airbags and seatbelts. Remember, because airbags are called SRS, secondary restraint systems. The seatbelt is your primary one. You've certainly changed all your brake force balance and dynamics within the vehicle, and this is where we've started in the last 5 years looking at PAS 301 to look at how things were the electronics copes as well as all of the actual hardware that's physically on board, like the suspension and the brakes and various other things. So it does get affected, and again we can see by looking at the CAN data on the vehicle how hard some of these systems are working and how they're trying to react to it. And again, we are definitely not within the parameters to which the OEM had wanted. Something off the internet, basically. But these, a standard, not standard, but quite a complex vehicle, all these sensors are not going to physically go back into the right position. They're going to be moved by the armouring process. And a lot of the sensors require very good positioning and so on. And we'll talk about it in a second. But once you've physically moved them, again, how they're actually calibrated or how they will work is in doubt, basically. Antennas. This is the RKE antenna from a Land Cruiser 200. This is the one that's by the actual gear shift itself. The furthest I've seen this antenna moved in an armoured vehicle is the boot. So this is designed to pick up that you're inside the Land Cruiser 200 as a driver or passenger in the front seats and basically detect you've got a key and then basically let you start the car. The furthest I've seen is the boot. You get into the actual car itself and it won't start. You've got to throw your keys in the back to actually start the car. If it doesn't go back in the right place, then you are affecting how the vehicle works. I'm an EMC specialist, and I hate going on about EMC because nobody really knows a great deal about electromagnetic compatibility. But basically, the EMC performance of your car is completely changed. It meets none of the regulations, and also you've got a big issue in the fact that you're going to fit non-OEM equipment and additional equipment and some very, very specialist equipment to the vehicle. And EMC is not being done on the vehicle. You don't know how the vehicle is going to affect your radios, and you don't know how the radios are going to affect the vehicle. And EMC is quite a big issue that we've seen. And the very last one is electrical power, and that leads us on to a case study, which is what we've been alluding to over the last day or so. So a few bits. We're talking about some power issues, and they were in Kabul, and they're on Land Cruiser 200s. and the fleet, which is run by somebody else for DFAT, had a number of problems on vehicles. Again, a lot of people have talked about mission profiles, etc., and we'll see that they're not particularly designed for what they were supposed to do because the mission profile has changed slightly. But basically, there's around about 17 vehicles, and the fleet manager at the time reported 35 dead batteries a year. What's a battery? Well, first of all, you've got to get them, and trying to get batteries in Afghanistan at the time wasn't easy. But the biggest issue is these vehicles were stationary or dead, as in not running for a period of time, because there was no spares that were available, and they kept going wrong. So it became quite a big issue within what they were doing. So we were asked to go and do an in-field assessment and put some recommendations together as to what we could physically do. And it became quite a nice exercise in that fact it wasn't just a very, very simple. I'm just going to go into some little basics, basically, about load balance before we even start. Load balance is about the amount of energy that we use on a vehicle in a certain mission profile, whether it's idling, whether it's doing 1500 RPM, about what the alternator and the battery can physically supply and keep charged. And this is just a little diagram we use in one of the training courses, which shows some of how we use batteries within the vehicle. So we've got two batteries, which I don't know whether this moves over. No, it doesn't. So we've got two batteries in the middle, which are basically what we call primary and secondary batteries. And you've got batteries in the rear, which are running equipment. And in this particular case, they're going through a DC to DC converter, not relevant to this particular thing. But basically, what we will say is the batteries power the vehicle. So we have to get this quite clear to start with. The alternator does not provide power to the vehicle. It's the batteries that provide the power to the actual vehicle. The alternator, its role is to keep those batteries charged, not the other way around. Batteries react very quickly. They can dump a lot of power very quickly with big inductive loads. They're there to start the vehicle and so on. They can change the way they actually operate very, very quickly. Alternators can't. They react slower. They're a lot lower power. And obviously that power then depends on how fast the engine's running and various other things, pulley sizes and so on. And another thing just to talk about there is I talked about primary, secondary, auxiliary. We define these, and we've used this definition for a long time. Primary is all about the car. It is about running all the equipment on the car and starting the car. The secondary we actually used for emergency, as in if the car won't start, we have a secondary battery. An auxiliary runs additional loads in the back, which may need to run when the vehicle is at low revs, or even when the vehicle is turned off in a mode where you're still running equipment. And the other thing before we just move on to this is when you hear that an alternator is a 150 amp alternator, that's when it's probably at its full operating speed. So when somebody says, I need 170 amps, and you fit a 170 amp alternator, I can near enough guarantee you, you've got to be running at 1500 RPM and basically generating that power by rotating the engine. So it's not a simple case of putting an alternator to match what you need in power. This is a typical type of curve for an upgraded alternator, and basically at the idle speed, this particular alternator is giving out about 200 amps. But when it's at full operating speed, it's giving out about 360 amps. And it's actually marketed as a 360 amp alternator. So again, if you want power idle, you've got to look at what the alternator physically does. So some basics there. So off we went to look at what the issues were. And the fleet manager in Kabul started to give us some information. He'd got no output power. Okay, fair enough. Cars don't start for some of the missions. And basically all sorts of various things came in the report. Battery management systems aren't working. He's unable to get any spares, and he's destroying his batteries very, very quickly. And he wants to have that, and the people who are paying the bills want to have that solved. So we went to have a look, and we got into Kabul, and we saw a number of things. There's a picture of this on the next slide. The batteries in these vehicles were starting to physically deform, and you could see them even after a period of 4 or 5 months. They were maybe 7 or 8 millimeters in deformation on the tops of the batteries. When we actually tested some, we were down to 5 volts when we did a cranking exercise on the vehicle. And some of them were only at 10 volts when they were just sitting there at rest. So there was obviously something wrong with them. Yeah, so we're on to a battery issue. We found 3 that were physically broken. Even the actual studs on the batteries, because a certain amount of additional kit had been strapped to them, they were starting to go wrong. And we looked at, again, something which is vital is the mission profile to which these particular vehicles were being used. And we did all this on one visit, and what we actually did was we fitted temperature labels all around the engine bay and onto the actual physical batteries themselves to understand what the temperature is. Now, what these actually labels do, you can buy them most places, they record the maximum temperature. It just goes black, and it basically tells you what the maximum temperature is achieved. It doesn't tell you how it changes over time, it just tells you the maximum. So we went back again. I think there was another visit in between, but we went back again. The batteries themselves hit over 100 degrees centigrade. And yes, you can fry an egg on the bonnet of a Land Cruiser 200 in Kabul, because we tried it. And it is exceptionally hot. The mission profile of the people who are using the majority of these particular vehicles was quite peculiar. I can't remember the name of the profile. I think it was diplomatic convoy type thing. They were taking people from one place to another. But the actual mission profile was they've got to keep the engine running. And the engine was going for around about up to 6 hours a day at idle, yeah, but only driving 20 kilometers maximum. So you had a lot of engine operation and a lot of things going on, but no actual driving, no cooling air going through. They were just sat there, often in the direct sunlight. When they were physically stored, and now that this is all gone, we can show the back end of where the Australian Embassy had all its vehicles. We had a very limited parking space, and I trawled through everything, and this was the only one I could find, but we've got one vehicle there which is in bright sunlight, and we'll see how that physically affected things as well. But basically, they were all outside, and a number of them were out like that. And the team operated a thing called a quick reaction force, quick reaction alert, and those vehicles were actually running in the sun itself. They were often running in the garage area. And Kabul, again, is a peculiar city. Well, not peculiar, it's 11th highest. It's quite high. It's a big solar loading, which hadn't been accounted for in that particular place. And there we have a picture of one of the actual batteries. And I don't care what battery it is, so it just happens to be Optima, and I'm not saying Optima anyway bad, that way around. But we were starting to getting, well, we had a lot of these. We had many, many batteries which were deformed. Basically that's caused by them overheating in some way and starting to gas. And what you actually see is that the shell of the battery gets softer and the pressure inside increases, and we get a deformation of the battery. When that pressure increases, the plates that we're trying to keep inside the battery together start to open up, and we get less of power out of the actual batteries. They absorb less power from the alternator, and so on. And some of them, and it does affect the way you go, is we had different batteries of different types in the same vehicle. That's not a design thing. That was the actual physical ability to be able to get batteries in country, where basically they could only get a gel battery or a lead acid wet battery or an AGM battery, and they just needed vehicles running. They all work at slightly different power levels and voltage levels and so on. And some, not all of them, but a couple of them had battery armour. And it's something I do not like at all, and we'll go into that again in a minute. So we looked at the batteries themselves, but surely it couldn't all be about temperature. So we looked further into what could be going on. And we started with how we actually generate the power. So these had the original OEM alternators on, which when we're actually at idle was about 50. There were about 110 amp alternators. Some were 70, some were 50, depending on which generation of Land Cruiser they were. But certainly not a big alternator. And when we went and did a load of testing on the vehicles themselves, some of them, with some of the equipment, were generating or needed a lot more power. And therefore, the batteries were sustaining what the alternator could give out. And talking to the operators, they often felt they needed to rev the engine when they were sat outside an embassy or something like that because they needed more electrical power. They didn't have a high idle system fitted. So anything they needed to do, they had to do manually. And basically, sometimes they forgot or didn't know. And because of all of this, the batteries and how they're actually running their profiles, the batteries themselves were getting quite heavily strained and adding to all the various bits and pieces that was going on. So obviously, we had a thing which we call a load balance. It's basically how much you need to how much you generate and store and when you need it. And basically, they weren't supplying that. So what was our solution? Well, no matter how we would talk to the Australian government, they're not going to change the way that they're going to do their missions. So that was not physically possible. We looked at the load balance and did a load of load balance calculations, and we checked with what the end user mission profiles needed. And we looked at what was required in terms of alternator batteries. The batteries themselves, as long as they're good batteries, were perfectly capable of doing what was going on. But the alternators themselves weren't good enough to be able to do that, and there was no way of automatically picking up what the voltages were and charging on keeping the batteries at the right level. We did battery armour, different opinions. From an electrical point of view, there's two things. First of all, you're going to overheat the batteries even further. And secondly, depending on how good battery armour is, and you have a gassing battery, you have a volatile, explosive environment inside because you're holding that hydrogen inside the actual battery box itself. And some of them, which are totally sealed, could be potentially dangerous. So I would say you don't. And in actual fact, on some of these, we looked at putting front armour and side armour and even bottom armour, but leaving the back and the inside towards the engine and the top actually without armour on, and found that that was a way of keeping them cool. We also investigated cooling mats and various other things, but you want something that's simple and easy. But we did move all the vehicles and changed the mission profile within the embassy itself. So they didn't park the vehicles in the sun, they didn't run them at idle in the sun, and they even put additional tarpaulins up, etc., to keep that direct solar loading off the vehicles themselves. So that was an easy one that way. So the fleet manager went out and bought all brand new batteries, so now we've got to keep them good. So we've done a bit with the alternators, we've done a bit with the power, and we've done a bit with how we actually stored the vehicles and so on. They basically used one of their ISO containers and they put an air conditioning unit in. And to keep the batteries good, we basically rotated the batteries every 2 weeks. So he would take two out of one vehicle, put them into battery bay, take two new ones out, put them into the vehicle. And whilst they were in the battery bay, we used a trickle charging system, and they were on charge continuously, just having a small amount of current, which is the best way to keep batteries charged. You don't want to throw lots of power at them continuously. And we kept that temperature at a nice, easy 21 degrees. And and they're 5-stage chargers. But once they've done their stages, they just sit there in a trickle. And we gave him some additional test equipment, some battery load testers. Simple things that you just put on the battery and they tell you the condition of the battery. So they could do, like Justin was saying, they could do weekly checks about how good their batteries was. And when they started to see one going a bit funny, they could take it out, put it onto charge and get a new one as well, put a new one from the bay in. I've already told you that the alternators are rated at idle, so there's some comments on power, etc. We do need to match the power generation to the mission. It's very difficult. A lot of people who are going to procure these vehicles, you're going to have different operating profiles, but some of them are quite extreme, and we need to understand what they are before you deal with electricals and sort out what the electrics are going to be. At the very beginning of this, one of the comments I was going to make was, the one thing that goes wrong on our cars as civilians at our houses is when we get up in the morning and the car won't start. It's about the only thing overnight that can go wrong on a vehicle which stops it starting in the morning. So we need to make sure we've got these things right at the very, very beginning. If you haven't got enough power coming from the alternators and you're drawing power, you're basically deep cycling your batteries. You're taking it all the way down to the bottom. And there are 3 types of batteries. The very last point on this, I'll talk about that. But basically, every time they go down to the bottom and then you're basically charging them up, you're stressing them. No matter what the battery is, you're going to stress them. So you want to be able to keep them in a good way to stop them going all the way down to the bottom and keeping them at a certain percentage. And once they are damaged, once you have dropped them and they start to get damaged, you can't repair the internal mechanisms inside the battery. They are broken forever. And at that point, they stop reacting to the changes in power that are required, and they stop taking charge from the alternator. So you're on a start of a vicious downward circle. Just another comment. We work with battery manufacturers and are starting to do some work on this. But basically, as we increase the temperature of a battery when it's operating, we have to theoretically, according to physics, reduce the actual voltage that we're charging them at. So the alternator doesn't really know that. It knows what current it needs to do, because that it's no problem with. But the voltage is going to put out the same voltage. There are some that are already looking at that in terms of vehicles around the world for the OEM, but not on these particular vehicles that we usually do things with. If you're going to need idle power, you've got to match that power to how you do it. And the easiest way is some form of high idle kit. Some vehicles have already got it. Some vehicles you're going to have to add something to the vehicle to increase it so you get the right voltages. And, if you've got absolutely everything on a Land Cruiser 200, absolutely everything, you can draw 70 amps out of the old Land Cruiser 200. And it's not that much difference for the 300 when we come to that. When we come to it, it's around about the 60 amps we've drawn out, depending on what you've got, how many things you've got on, and that's just the OEM vehicle itself. So a few comments on batteries. They don't like heat. If you talk to a battery manufacturer, they'll tell you -40 to +55. There's a totally different way a battery works. At -40, it'll give you all the power it's got, but it won't accept that power from the alternator. When it gets higher up, it just won't start to give you the power, and you start to actually deform it, gas it, and various other things. And if you're charging it at higher voltage, you are actually producing more gas, and you just enhance the way they break. The pressure increases inside, it deforms all the softened cases. You lose the pressure, the plates come apart, and basically you're losing the capacity over the period of lifetime that you're operating. You can see a downward spiral, but every now and again you'll see a drop of 2.2 volts or something like that. And at that point, you're losing complete cells in the battery. And once they start to go, you'll lose the next one and the next one and the next one. And we talked about putting them into boxes, etc. The AGM batteries will, once they get to a certain internal pressure, they will release hydrogen. And it's around about 2.5 bar internally. So once they do that, they will start to dump hydrogen out into the atmosphere. It's hydrogen, don't put it in a box. Another comment about batteries, don't mix the technologies. So there are 3 main battery technologies that you may hear about: AGM, gel, and basically what we've got in our cars, liquid lead acid. The gel battery is fabulous at deep discharge. The liquid lead acid is brilliant at starting a car. The AGM is 95% of both, let's put it that way. So it's a good all-round battery. It's all the electrolytes inside the glass mat. You can put it on its side. Theoretically, it's air transportable with certain other precautions. So it's quite a good one to which you can use on vehicles. But you wouldn't put an AGM with a gel or a gel with a lead acid. You would keep that technology the same. So after a year, the fleet manager had lost 2 batteries and he'd lost 1 sortie from electrical failure, and that was the battery terminal coming off. So we basically reduced the amount of money they needed to buy on batteries. We'd reduced the sorties that they'd lost through electrical faults on the vehicle, and basically, hopefully, made life easier for them to operate for the Australian government. So that's just a very simple thing that we've been involved in terms of power and solving problems in the field. So the last bit is all about the Land Cruiser 300. We've all seen it, we've talked about it, we've done all sorts of stuff with it. It's quite, it's a little bit more advanced than the 200. I can stop it from starting with a device no bigger than my mobile phone. I can stand by the side of the car and I can stop it starting literally by generating a certain amount of RF energy, and it'll stop. Well, it won't stop, no, it won't start. It is very difficult to stop a car once it's started. But when it's in the starting phase, it needs to get all the protocol together, it needs to talk to various different things. And if you can interfere with that, you can physically stop it from starting. And again, we've, on the Land Cruiser 200, seen that all over the world, and you've got to do something about it if you're going to put high transmitters, power transmitters, electronic countermeasures, HF, well, not so much HF radio, but various things on the vehicle you're going to have to do. And if you're going to go into electronic countermeasure bubbles in certain areas, there is a chance it's going to be affected. There's definitely more, as other people have said, there is more going around this vehicle in terms of CAN and LIN messages than any of the Toyotas before. And some of them are getting very, very intelligent, shall we say. They will do things if you don't do something else. If you do something wrong, they'll correct you. There are things that are going on inside. We're now talking to the alternators. There's all sorts of various other bits going on inside there. Yesterday we talked about the electrical braking system. Yes, completely new. It's there on the Toyota. It is a park brake though. You've got to remember that. It's designed to come on automatically if you want it in auto mode. It's designed to, not take the stress out of putting the handbrake on, and it's supposed to automatically release when you press certain pedals and certain operations, take it out of gear, or put it into gear and so on. It's certainly lighter, and in the past few months, we've seen that it far exceeds, in certain configurations, the weight limitation on the tyres that it's physically got. So it will easily go a lot faster than what we can actually put on there to hold the payloads on the vehicles themselves. This is a test we were involved in. And this is a stability thing. We actually physically collected all the CAN data. I can't tell you what it's all about. I can't tell you anything about it yet. But basically, yeah, the electronics on board are struggling at that stage, but they're still physically operational. In this particular case, this particular vehicle had a configuration of mechanical parts on it which didn't fit its configuration. And the owner of this vehicle basically changed the way they were doing. So they were looking at what configuration of brakes, suspension, etc. would handle best on a 5.1 ton vehicle. And this one didn't, as you can. Well, I hope you can see the front left wheel was about 12 inches off the ground at one stage, and all the occupants and my fabulous wife at the back there was shouting down the radio, "Stop, stop, stop, you're going to crash." And we actually did feel we were going to go over in this car. But that's that particular configuration to which the owners of the car now know what they're not going to do in the future. Massively less space inside the car and in the engine bay. So it's going to be very difficult to do certain things for the electronics inside the engine bay and inside the vehicle for the 300. The 200 have dual alternator kits. They're not available yet. For the 300, we've got to look at how you can get the space in the engine bay to give additional power. And even putting a second battery in some of the vehicles is difficult. So we are looking at smaller starting batteries, smaller secondary batteries, just to take the same space as what we had on the original battery itself. It does have an increased alternator output. And basically that alternator output is a lot bigger than the Land Cruiser 200. But we already know that certain people's requirements for this vehicle, what they're going to fit in the car, the alternator is not going to be big enough for the additional power requirements. So there are already alternators which will take us up above that particular requirement. So the only one thing I would say to any manufacturers here about electrical and what we've just talked about, as I basically conclude, the only thing I would physically say, which I sort of leave as a comment on this, is if you're going to specify a vehicle and you're going to make a vehicle, I always say put a battery isolator in. Not a battery management system, but a full mechanical system that you can turn on and off. You can protect everything at night, you can turn things off for flights, you can do maintenance a lot better. But if you haven't got that battery connector, it's a lot more difficult to do so. So that's a brief introduction into some of the things. I've tried to do what Rob asked, which was in his first slide yesterday, which was let's make people aware and let's move forward in time. So I've tried to make people aware of what's happening with electronics on vehicles, given a case study, and then giving you a flavour of what we've found so far on Land Cruiser 300. And I'm open to any questions or comments at this time.
Thank you so much. That's brilliant. And I have to say, as somebody who's responsible ultimately for that operation in such a critical area such as Kabul, that the lesson we were taking out is that something that is not necessarily given the credence, being the battery system, electrical system, created such challenges that we were having ambassadors call up to Canberra to say, this is just not good enough, find a solution, and eventually that we did. But it again shows that, in the element of a $200,000 vehicle that's gone through significant engineering modification and construction, sometimes it's just the very small item that actually will trip you up rather than the very large items along the way. So all lessons learned, part of the challenges of keeping the fleets on the road.